Hey everybody, it is time for activity. Do we have anyone in the chat yet? Let's make sure MuBot is awake. Now we're going to start up some activity and go over how to do some of the functions we've been doing this week. And it will definitely help out a lot with the assignment. So if you've been working on the assignment or you have questions, plural, this video is for you as we get MuBot wide and awake. So let me know your questions. I'm going to pause this right here. Let's go ahead and get the activity going. So let's go over here to the BAS 320 page. Any questions you have? Great stuff right here. People are already working on the assignment due on the 26th this weekend. Here we are going over to the activity. Activity number 4. Let's go take a look at this. See, MuBot's awake. Got the activity we're downloading. And here we are. The activity is open. I'm going to clear off the screen right here. Get everything nice and neat. Situated in R. If you're in the chat, feel free to say hi. Is anyone here yet? No one's here. No! I said I was starting in 5 minutes. People might be arriving shortly. Oh, just to get ready here. Get ready for the weekend. We'll do some activity, then it'll be the weekend. Be awesome. Today is activity part 2 for associations. And if you're in the chat, say hey and code along and ask those questions. Be like, hey, what does this mean? How do we read this output? Important stuff right here. Let's go take a look at activity part 2. So this is all about associations. When you hear an association, you should think, when we know X, it tells us something about Y. So things can be associated in a lot of different ways. We're just looking at a lot of different stuff. Do we still have any of them up? Maybe not. I cleared off all my plots. It's a bummer. We'll look at some associations here in a moment. But think about this. If you know it's Christmas time, then what might be available at Starbucks? Probably some peppermint drinks or stuff like that. Some Christmas-related drinks. So when you know what time of year it is, like let's say it's right now the fall. So if I go to Starbucks, I just want some peppermint. I want some pumpkin spice latte. So if I go by Starbucks right now, going to see some pumpkin spice latte because it's associated with the time of year. Knowing what time of year it is tells me something about what will be available at Starbucks. That's what an association means. What's available at Starbucks is associated with what time of year it is. I know what time of year it is. That gives me information about what is available. Now, you might say, well, I went to Starbucks and they didn't have pumpkin spice latte. It doesn't mean they will have it. It just means we would have more information we would know. Like people who study would be more likely to make an A. That's one of my favorite things to say. If you study, it's associated with making an A, but you're not promised an A if you study. It's not like people who study do make A's. People who study are more likely to make A's, thus studying is associated with making an A. And so let's look at some of these associations right here. And we're using my favorite data set of all time, Survey 10, top tier data set right there, my favorite. And we're going to run what's called a correlation matrix on the first 7 columns. Now we're seeing something interesting right here when we run this correlation matrix. So we have to get, that's telling us to do it. So let's see how to do this here. Are you ready? The first thing we're going to do is we're going to load library reg class. If you do not have library reg class installed, you will need to install reg class. I'll go ahead and show you what it looks like. Installing reg class goes to the CRAN server. These are not errors. It's telling you that it's being downloaded. And now that it's downloaded, it is on your computer. So now you have the reg class package. Probably comment this out. I'm going to put a hashtag before it with Control-Shift-C, which is a quick way. Computer. It doesn't want to do it, so we won't. We'll do it the normal way. So we can put a hashtag before it right here, and that will comment it out. It might have been mad because I had that there. Yeah, it looks like it was. This is quick comment on comment, Control-Shift-C. Love my quick keys right there. So now that we have the package installed, that just went and downloaded it from the interwebs. So now that we have it downloaded, we want to actually load it up. To load a package, we want to go to Library. Notice how it changes colors, telling us that this is something special we're doing. This is a function that loads your libraries and attaches them to your R, which means we just have access to the things inside of them. And we're loading the reg class library, which is a package right there. That's what those P's stand for. And we're going to load it right here, and then we're going to hit Control-Enter. Runs the code, and that's just more like, hey, did you know this is happening? I'm loading these required packages in. This was built for under R version 4.1.1, all these things right here, and there was updates to functions, which we'll be using later on. That was just a bunch of messages. We don't even need to see those. They're gone now. So what we're going to use is data survey 10, and data survey, or survey 10 data, is inside of your data sets now. Data is a function that loads data sets that have been attached to your R that you have access to. These are all the data sets you can use right here. They're from different packages. Some of them you might have, some of them you might not. Like you might not have R part loaded in or random forest, but you could load any of these in. You notice we just passed the surveys. It will autocomplete, so we can go to survey 10 and just go here and hit enter and then hit control enter to run it. Now I want to mention when I'm hitting control enter, it's sending it down to the bottom console. It'd be the same thing as me going here and literally pasting it down here and running it. But by hitting control enter, it runs it in the bottom console. If you're down here in the bottom, you do not need to hit control enter. You can just hit regular old enter because you're not sending it to the bottom console. This is just where everything evaluates, and this is where you get to like write all your code. So we've loaded in survey 10, and we want to make a core matrix. I'm not the biggest fan of the core matrix. So you see right here, core matrix auto completes. It's going to make a correlation matrix of what we want. And we only want the first 7 columns. And it tells us the code on how to do this. But let's make sure we know what the code is saying. Right here, what this code is saying is we have the survey 10 data set, which is just an Excel spreadsheet. Think of it as an Excel spreadsheet right here. That's just an Excel spreadsheet, just rows and columns. And the first space right here is going to be your row space. This is where all the rows are. And then over here, this is where all the columns are. The comma separates the columns from the rows. Important to know that the square brackets are how we get vector positions or positions in a data frame in this case. So we're taking all of the rows and columns 1 through 7. There's the correlation matrix for it. Now, if you notice something weird right here, we don't have 7 variables. Kind of weird, right? Oh, I'd throw out 100 points if anyone knew why we don't have 7 variables. When we do correlation, we can only do it on this. And that's a 201 question. 320 question also. A lot of classes use this knowledge. Correlation is only a specific type of relationship between 2 types of variables, or the same type, where both variables have to be this type. The first 7 columns, which you can view right here, have in it gender, height, weight, desired weight, GPA. And you notice gender is the only one not appearing over here. As we look at the kind of connectivity of the correlation between these. We can go right here and look at the correlation of desired weight and weight, and it has a correlation of 0.874, which is a very strong positive correlation. The positive indicates the direction. The closer it is to 1, the stronger it is. And we do ignore these ones that are 1 right here because that's the correlation of height and height. So X is correlated with Y if it's the same variable 100%. And so we don't care about that one. I wish it just put NAs for those. But why don't we have gender? Correlation is only between 2 quantitative variables. So this function right here is smart enough to know not even to run the correlation because we can't do correlation with categorical variables. So since it is a factor, you can see over there it says factor, we get that. We'll actually get the same output right here if we just do 2 to 7, and the output's identical because it just skips over that first column. It says, nah, I'm not doing that right there. So now we want to run all correlations on the entirety of the data set, but why didn't we just do that here to start? And the answer is, and this will now do the full data set, if you had done this on everything right here, you'd get this. Not liking this. So that's our little bit on core matrix right there. Let's make the part of this video called the core matrix function. So Brian, future Brian, that's the core matrix function, how to make correlation matrices between 2 quantitative variables. Almost said the wrong thing. But now we're going to talk about the all correlations function, which is one of the cool functions we have inside of Reg class. Just a moment ago, you saw that the correlation matrix was turning out this ridiculously large matrix of stuff that is just too much to read. Well, the all correlations function is going to fix these up for us. It's going to make it a lot better right here. When you run all correlations, the first thing you're going to give it is a data frame. The data frame is just an Excel spreadsheet. So we have here the rows. The first person was a female who's 6 feet tall, weighs 160, wants to weigh 155, GPA 3.7. This is all the information on these individuals, and we're going to put that data frame right here. Now, as the name says, when we do all correlations, it's going to find all the correlations. So now we run it, and it literally just found all 136 correlations. And it doesn't do X, Y, Y, X. It only does it one time. Like if we did height and weight, it wouldn't do weight and height. So it only does one permutation of it, where the matrix before would have a symmetric shape to it, if you know some mathematics. So what's really great about this is we just have it all here in just a long list, and we could even save this as a data frame and try to manipulate it. But here you can see the correlation between each variable listed out in probably a nicer to look at format with variable 1, variable 2, the correlation, and then the p-value for each one, which tells us the statistical significance. So we can see here, a lot of these are statistically significant. Like GPA right here has a statistically significant correlation to someone's height, and it's negatively correlated. Maybe the males, I don't know. We could control for the looking variable. We could look into that. I don't know. I was not helping GPAs in any way with my GPA. But people, generally, we see a negative correlation that taller people generally have lower GPAs. And this is statistically significant. But you might say, Brian, this is still too much output. You still have way too much output on the screen. Like a little tiny bit of code right here. Tons of output. And we can fix this, though, with some of the new arguments. An argument is an additional bit of instruction. So when you look at an argument, you're saying, get me all the correlations for this data frame. The first argument is, what do you want all correlations for? The way to make a new argument, which is taking a breath and being like, and then do this, is to put a comma right here. So the comma is going to be a new kind of like, what do we want to do next? So now I'd like you to, and let's see what it says. I'd like you to sort it, and sorted is how we're going to sort it. It's like, this is going to be sorted, and look, it tells you, here's your options. So right now you can do none, which is the default, strength, significant, or magnitude. That's my favorite right there. And we're going to do sorted, and be very careful. You have to put this in quotes. It is a string, and do spell it properly. Strength right there. So here we are. We have sorted it by the strength, and let's take a look at what we get now. Taking a look at what we get is now sorted by strength, and you can see right here the correlation at the very top of the list is the most negative. As you go down the list, they get closer to 0, which is the weakest, and eventually at some point they go through 0, and you'll notice these are the weakest, and thus the p-values are closest to 0. Now you might be saying that doesn't look like a p-value close to 0, but watch this. It is, and I'll show you. We're going to store this as a data frame for just a second so I can manipulate it, and we're going to take, I thought I did. Oh, that's the core matrix. Whoops. Core matrix, go away. I was like, I did. Core matrix won't let me store it as a data frame. There we go. We're going to take the p-value. We're going to round the p-value. We're going to overwrite it with a rounded version of our p-value to 4 decimal places. Okay. Let's relook at the data frame. And here you are. Go a few more decimals on this. 7. Don't give me scientific notation now. Did I overwrite it? There we go. Oh, I got to restore my matrix because I already overwrote it once. There we go. So it was in scientific notation before, and take a look at what we have right here. These are the strongest correlations, and i.e. they are the most statistically significant. And there does come into play like sample size and power associated with this, but these are all coming from the same data frame, so they have similar sample size, and there's other things to take into account, but it's almost tomatoes to tomatoes. It's tomato to cherry tomato. Very, very similar stuff going on right here on how these are calculated. So we do see a similar relationship that when the correlations are very close, they're close in significance. But once again, this is the same data set. You cannot automatically figure out the significance from the correlation. There's other factors that go in, like how much data are you analyzing to figure out statistical significance. And so you can see right here, the strongest negative is between somebody's desired weight and how many body piercings they have. Where generally we see people who want to weigh more have less body piercings. So there's a negative relationship right there, which kind of makes sense. Maybe lurking variables, maybe it's guys, I don't know. I want to weigh a little bit more than most people probably because I'm 6'3", so maybe guys. Then you go down here and you see we get to the not statistically significant. Once we pass this threshold, everything down here is probably just due to random chance. So if someone said, did you know there is a negative correlation to how much people play video games and their GPA? It's negatively correlated. You play more video games, your GPA is negatively related to that. You say yes, but that is probably by random chance. They say, but it's 0.09. That's close to 0.05. And you say, too bad, it's not 0.05. And we don't even like 0.05. We like those low p-values. We want the ones down here where we say desired weight and weight are super correlated. Kind of nice that if someone's desired weight would tell you a lot of information about how much they want to weigh. Someone's height would also tell you a lot of information about their weight. Very strong correlation here. And these are the strongest positive. So if you notice when we sort by strength, it's going to sort it from the most negative to the most positive, and zeros towards the middle, which are the least statistically significant. But there is a better way. My favorite way of doing this is to go to magnitude. And when you sort by magnitude right here, and I'm still doing my p-values nice and neat on the side, it should sort it by p-value, or absolute value of correlation, I believe, which is basically going to be p-value. Look right here, we have the strongest correlation, and then you'll notice it goes negative, but negative is here because negative 0.588 is stronger than positive 559, but weaker than 0.60. The absolute value of the correlation is how strong the correlation is, and you'll notice that the p-value starts to get bigger, i.e. when the correlation gets smaller. And look at here, the correlation closest to 0 is the one that is most likely by random chance, i.e. we don't see any correlation between how many tattoos people have in video games. I've seen some gamers who got like a full sleeve of Mario, but apparently there's no correlation between this. It's just all random chance. Like if someone has a lot of tattoos and plays a bunch of video games, just random chance. Someone has not a bunch of tattoos and plays video games, random chance. There is no real association between these two variables. So we've added this in right here. You can add in whichever arguments you like, but important to know. But maybe we don't want to focus in on all these variables. So now what's really great about the all correlations function is rather than focus in on all of these variables, we could focus in on just one. I want to make clear here what you're writing. So I'm just going to write from scratch again. All underscore correlations. Hit enter to let it autocomplete. Always use your autocompletes. They are a lifesaver. Now we're going to type SUR and we'll go autocomplete to survey 10. Now we're going to hit comma, and I like to hit enter sometimes because then it puts it on a new line. So we can just be like, this is the next thing we're telling it. We're going to do right here, sorted equals magnitude. And this will sort by the absolute value of the correlation. And then we'll go here to interest equals, and you have to put this in quotes, capital GPA, and make sure it's spelled properly, and it has to be in quotes. If you don't put it in quotes, it's going to get angry, and look for the object GPA, which is not currently saved here. This is a vector GPA inside of the Survey 10 data frame, not an object GPA. And so we click right here, and we get only the correlations with GPA. Now, it doesn't have to be in just the first one right here. It can be in the second. It does the pairwise, and it doesn't repeat once again. But these are only the correlations for people's GPA, and we sorted it by the absolute value. So the strongest one is at the top, and the weakest one is at the bottom. It is closest to 1 or -1, which in this case, -1. Someone's GPA is negatively correlated with their weight, and something tells me probably, and I could show you, if you don't believe me, you're saying, Brian, just because your GPA was bad doesn't mean, I don't know. Let's take a look right here. Let's go here and investigate and go to a subset. I'm going to call it males. So we're going to go to males, and this is how we can see if we control for males, we shouldn't see this. So I'm going to go here to gender equals male, and this is only going to make a subset of males. And then we go right here and we go to females, and we make a subset of females. Got to change something. Too quick with that copy paste. And then we see right here GPA and weight. Oh, wow. Brian, you were wrong today. 50 points if anyone's watching. But how about females? Is it negatively correlated for females? The answer is, well, I'll be. Wow. I thought it wasn't. I thought I'd done that before. Maybe I hadn't. But, give out the place there. But yeah, for both groups, but I think it had a stronger. That's 0.009. And that's 0.01. Yeah, it's way stronger. It's way stronger. Yeah, it's way stronger. That removes some of the variation. This is the strongest, negative 0.21, and then this is weaker, smaller data set, so less significance, and this is weaker. It took away some of the significance, so that tells us that even though it is statistically significant for, I think, might have been for both. Let me double check the p-value on this one again. Yeah, that is statistically significant, 0.01, 0.016. Make sure to know your scientific notation. It always gets me a little bit when it shows this. I wish it just didn't. That's why I round my stuff. And so there it is right there. You can just copy paste the numbers sometimes, but if they're really small, it's going to be way further over. So make sure you know that that is 0.01 and how to count the zeros right here. So by seeing the e to the negative 02, you should know count the leading zero, and then there's 2 zeros if you count the leading zero. So when you see something like this right here, this would be point, and let's write it down just to make sure practice. 1, 2, 3, 4, because that's 5 leading zeros right there. So this number right here, if we run it, will turn out to that right there. So that's the number we just saw up there. Make sure to know that and to tell if something is statistically significant, because I've had people tell me, unfortunately, this p-value is not statistically significant because it's 7. P-values can only range between 0 and 1, so you should only see p-values between 0 and 1 unless we're doing some sort of scientific notation. These are still between 0 and 1, but they're just notated scientifically. Just make sure to see that. That's a very common error I've seen. And so, yeah, that's the correlations right there, looking over Survey 10. The analysis you have done so far has assumed that Pearson correlation can describe the relationships, but we have a different type of correlation called Spearman. Now, when it comes to Spearman correlation, when do we use Spearman correlation? The utilization of Spearman correlation comes into play when we have issues with nonlinearity. Let's take these down. Nonlinearity. Let me put a break. Talking about some Spearman correlation right here, and when would we use Spearman instead of Pearson? So here we go. The ideal Pearson relationship has a few characteristics. An ideal Pearson relationship is 1, linear. 2, no outliers. QQ straighten up, no outliers. It's got to be quantitative variables to do correlation. 3, minimum heteroskedasticity. Might have spelled it properly today. So when you get down here to the ideal Spearman, there's a few things that changes. 1, must be monotonic. So it must be monotonic. Monotonic means it goes in one direction. So the plot needs to go continuously up or continuously down. It can't go up then down like a rainbow. Someone say rainbow? Where's my rainbow effect? So it can't be like a rainbow. No rainbows today. What'd I do? Oh, I think I gotta fix my button. Worked so perfectly. I have too many buttons. So it must be monotonic, go in one direction. Also, 2, handles outliers. That means it works with them. It can be fine. Handles outliers. Handles heteroskedasticity. And that's got it. So when would we use Spearman? Probably the biggest thing is to use it when it's not linear or has outliers. So Spearman is going to be best used when there's when we have outliers or there's a lack of linearity. And we can see some of this. I'm going to show an ideal relationship right here, which probably is going to be better with Spearman. If we go to the same data set we're working with and use height weight right here. So this is the association function right here. The association function uses y tilde x comma data equals data frame. So the data frame I'm using is the Survey 10 data frame. The x variable of interest is weight, which is inside of this data frame right here. There's the weight. And then the y variable of interest is height. So that's saying make an equation from height, weight. That's the formula format, y tilde. Tilde is on the very top of your keyboard over here under the escape key. That's a tilde over there. Next, number 1. And so height tilde weight makes the equation height explained by weight. So height will be on the y-axis. And then we are using the vectors from inside of the data frame Survey 10. This is really cool because it'll run all this code for us and make this plot. And remember those notes we just took? If you look at this right here, you will see there's some nonlinearity. This does not really follow a line very well. It goes up and then it bends. But that's good because it goes up and then it bends. It goes in one direction. Kind of reversed image right here, but it goes in one direction right now. It doesn't then go down. We don't want it to go down. We want it to continuously go up if we're going to attempt to use Spearman. Also, we have down here the presence of some outliers, things that are far away from the trend. Maybe some minimum heteroscedasticity, but a little bit of spread. There's maybe just more points creating a little bit more spread, but overall the issues do seem to be not much heteroscedasticity, presence of some outliers, presence of nonlinearity. Good candidate for Spearman. Now, this is not the way to decide it. But when you see that the Spearman is probably a better relationship visually, which we do see in the graphic, when you look at your output for the values, Spearman usually comes back with a little bit stronger of a relationship. And what Spearman does is it's a rank relationship. Spearman takes all these values and turns them into the rank. So the highest value of somebody's height would become 699. The lowest values of someone's height would become 1. And think about that. Let's say we had a giant in the data set. Let's say someone was like 10 feet tall. Well, then they'd be number 699. So if you're an outlier, it downweights you. Let's say Brian weighs 500 pounds. Well, then when we rank Brian, it doesn't matter. Rock, what do you think?
It doesn't matter.
It doesn't matter if you're an outlier. You become 699. So this is why it can handle outliers, because it's going to rank everything. Rank correlation. And by ranks, what do I mean? It means you put everyone on a line. You say, okay, you weigh the most, you get rank 699. Okay, you weigh the least, you get rank 1. And it'll handle all the ties and everything for us. It'll do all those calculations. But just remember what that does. It doesn't matter if someone weighs 800 pounds. They will still have rank 699 if they're the highest. If someone weighs 500 pounds and they're the highest, they're rank 699. So you can't really be an outlier with Spearman rank correlation, because everyone gets turned into ranks right here. And then we do the correlation on the values of the ranks. So with this right here, we must make sure the ranks go in one direction. That's the monotonic condition right here. And it also does well at handling the heteroscedasticity, because the furthering spread is also sort of an outliers issue in its own right. So we can get both values right here, and we do see that there is a better Spearman relationship. We can also do this with the all correlations. Rerun it from Command B, but the argument type equals Spearman. So let's go grab our all correlations right here and look at the Spearman. Let's kind of compare and contrast. We're going to change the data set back to survey 10. Once again, we have 3 arguments right here. Let's read it. I want to get all the correlations from my data set survey 10. Sort them by the magnitude of the correlations, and I'm only interested in looking at the GPAs. Now we want to add in one more argument and say, give me a certain type of it. Make sure to use your autocomplete, and then look what it says. We have the choices of Pearson, Spearman, or both. And I think it gets a little bit mad sometimes if you do both, if you ask for sorted certain ways, because I think you can't sort the p-value on those. So let's go here to Spearman. And was it capital Spearman? Oh, it's mad. It's lowercase Spearman. You entered Spearman. Oh, I'm sorry. Does magnitude do that now? Oh, magnitude still will not correct you if you spell it incorrectly. So watch out. Unless Dr. Petrie did... Nope. I thought he might have corrected it. I thought he might have did like a 2 upper or 2 lower, if you know what I'm talking about. There's ways of fixing that. So with this right here, you will see we have, and it looks actually magnitude. And this is the Spearman. Is it sorted? I'm a little worried right here. Let's take a look. Let me only run this. Doesn't look right to me. Magnitude. We're going to fix, I think the sorted, I might have a typo on. Sorted. Magnitude. Magnitude. There we go. Okay. What's that title? Magnitude. Oh, did I still have a capital? You gotta be kidding me. Capital M. When did I do that to myself? Wasn't doing that earlier, was I? Good, good, good. I think I was changing my code to show bad things, and then I did something, and always look at your output. Even I make mistakes. Happens. I make a lot of mistakes. Like that. So here we are. This is sorted by magnitude and is now no longer Pearson correlation, which is linear. Highest Pearson correlation being negative 0.2146, and the highest Spearman, which is actually stronger. So the desired weight GPA actually looks to have some sort of non-linear relationship. It's picking up on it. So I'm going to go over here and I'm actually going to plot it. And I want to see it because there's a negative non-linear of sorts. And, oh, more of it's an outlier issue. You can see it by my head right there. Maybe it's more of an outlier issue. You can see the difference between the Spearman and the Pearson. Spearman's picking up on it a little bit more. It's probably downweighting those extreme outliers. And like we said, outliers are not something that Pearson handles well. This something, the GPA is going a little bit lower as desired weight goes up. I could reverse it. It might make better sense to say desired weight, but we will still see the same values because it's just reversing the axes. It's a little bit easier to see, and there's the low outliers. Can people really have a 0 GPA? I wonder. They might just have not put in their data. So we could go here. Yeah, sure. Let's have a little bit of fun. Let's go here and go to Survey 10 and go to GPA. No. Let's go to GPA. Really? Where's my autocomplete? There we go. Equals 0. These are the people who have a 0 GPA. You can find them like right there. Then we're going to go to which. This will give the position of these individuals. So there's the position of the individuals. And then we're going to go here to Survey 10, $GPA. Now that we have their positions, we're going to go to their positions. And these are the values in their positions. And then we're going to overwrite it with missingness, and they're gone. And was it really the outliers causing that issue? Yes, it was. If you look at the new output right here, which is what we said it handles. Do these people really have, and now these values are close, which if there's not really a difference, probably go with Spearman. Go with Pearson. If there's not much of a difference, because it's, when you look at the plot right now, it's mostly linear. It's got some-ish outliers. It's just not a really strong one. The R squared on this is a little less than 9%. How do you get R squared? You take the correlation and you square it. I know it was negative, but negative times negative is positive, so it's a little bit less than 8%. I was doing 3 times 3 is 9. Carry decimal, you get a 0.09. And so it's not that strong. Is it practically significant? Probably not. Is it statistically significant? You bet it's statistically significant. This is where we get into the point of like, it doesn't really give you that much information. Knowing someone's desired weight wouldn't give you that much information on their GPA. There's a lot of variation, especially over here. We have very little data for people towards the 300-pound range. So, and this is a desired weight. So do remember that this is not how much people weigh, which is totally fine. I mean, know a lot of guys like my head, but like I want to weigh 250 or 220 or 230. So if someone was like 6'7", 6'8", they might want to weigh 280 or something like that. So that's a desired weight right there. We could also change it to weight pretty quickly. I'm going to go back here. If you've been doing what I've been doing, I'm going to reload my data set. The reason I'm doing this is I just overwrote some values. So since I overwrote values, I kind of want to go back and not have that and go back and use the original data for any problems I do. So if you're following along, you might want to do this too. If you've changed your data and you ever run into problems, just rerun the data right here and it'll reload it. So you could also clear your environment and reload the data. And there you go. Reloads in. Nice and neat. It's there for you in case you break it. But be careful. There's no undo button. I had to redo. There was a redo button. So let's do another topic right here. Here we go over here to the next topic. Which variable has, check it out. Let's check out the next topic right here. We've got all different things about make a scatter plot of the relationship. Same sort of syntax as what you use for association with the plot y tilde x data equal, and determine if you should use Pearson or Spearman to gauge the strength. So once again, which variables are we doing? Which pair of variables has the strongest negative? So I think we're using this right here, strongest negative. I think we just looked at that, didn't we? Strongest negative correlation. And if we're doing the Spearman, bring all correlations, add the Spearman. So we do have a scatter plot right here. And frankly, so this is kind of the same thing we're doing. You can see what's going on right here. Let's look at I'm going to show you the graphic for it again, the actual graphic. Here's the actual graphic. And one thing should jump out to you right now, these outliers. Here you go. There's a drastic difference between the Pearson and the Spearman, which is not really how you should look. You should look at these outliers and say, these are drastically impacting the Pearson. And we should go with something that downweights these outliers. These would actually all be valued at 1, and everything else, because they're going to turn into their rank when we turn them into a Spearman rank correlation. So we can use the plot also. We'll get a very similar plot, just the same sort of syntax as we have up here. So we're just going to do y tilde x comma data equals. Our y variable is GPA. Oh, got caps lock on. GPA, our X variable is desired weight. Make sure it's got a capital. And then the data frame is survey 10. And we get the same sort of plot. It's a lot easier to run the associate function. I just like doing that because you get all your output right there in one spot. So the association is highly statistically significant, but there is obviously no cause and effect, underlying relationship. Why do you think there's such a strong relationship? Probably gender going on right here. Maybe. We could control for it and look. Let's mention one last thing right here. This is important stuff. It's important to know what all your output is. So just take a moment right here and let's talk through the output. In this output, we get the value of the Pearson correlation. We get the value of the Spearman correlation. Both of these have a negative correlation. We get the estimated p-value for this relationship. And when you get an estimated p-value, it's because we're doing what's called the permutation procedure, which is behind me right here. We go in, look at our value of correlation, which is here on this dark red line, and then we make random permutations, which are just randomizing our data and seeing what values of correlation we get by random chance. Now, the most likely values of correlation by random chance are very close to 0. I can make this distribution look a lot smoother by adding a new argument here, permutations equals, and going to something like 10,000. A little bit ridiculous right here, but what it's going to do is actually going to make 10,000 random data sets and find the correlations, and a lot of those correlations were close to 0. Now, we did not get any results that were as extreme in terms of absolute value. That's why it does a dashed line on the other side as our Pearson correlation or as our Spearman correlation. If we want to find something outside of it, we'll actually have to take a weaker correlation like this. So let's look at a weaker correlation right here and see one that would give us a result for a p-value that is not going to be 0 right here. So now we run this. The p-value for this, and that's not a good one right there. Oh, wow, we get a huge p-value. This means if you look at this graphic right here, let's show it, about 83% of the results are outside of these red lines. Here, let's make it nice and neat above this, and let's stretch it out really big. So if you look at that histogram right there, the red line on this histogram outside of this and outside of that, not the inside, that's only like 17% inside of it. Outside of it would be 84%. So that's about 16% inside and 84% outside. You notice this one's a little bit bigger on the inside, so about 28-ish, 29-ish% on the inside, and then 71% on the outside, telling us that this correlation is likely by random chance and this correlation is likely by random chance. That's what the p-value is. And if you're wondering, well, how is this being calculated? Let's bring it down to just 2 permutations. Notice that both of these permutations right here and right here are as extreme or more extreme than these values, which gives us a p-value of 1. Notice right here that the permutations landed inside, so none of them are as extreme or more extreme. This is done via a randomness procedure, and in this instance, one of the permutations on the Spearman was inside, and one was more extreme. So 50% of the permutations were as extreme or more extreme. Here, 2 out of 2, 100% of the permutations were as extreme or more extreme. It's harder to calculate if you keep doing more, but you can see right here, well, here's 2 inside, 3 outside. So 3 out of 5 is 60%. Here's 1, 2, 3, 4 outside, and 4 out of 5 is 80%. And you notice if we just keep going higher, there's going to be more and more, and it's going to tell us the percent of permutations that are outside of this. And if we go to more extreme measures, we can go right here, and it's going to calculate a really exact p-value. So 83% of the random permutations were as extreme or more extreme than ours, telling us these are by random chance. Ours looks to be by random chance. But to contrast that with one that is not by random chance, if we went here to desired weight and weight, now we're going to get a ridiculously strong p-value. And you notice right here, this is one that's not by random chance. And what's really great, if you look at this right here, is this Pearson or Spearman? Is it linear? Yes. Is there an outlier? There's a strong outlier there. Is it heteroscedastic? That's very heteroscedastic, and that's maybe some outliers. So this would be a very strong candidate for which one? See if you know. Since it does have heteroscedasticity, since it does have outliers, and it is linear mostly, but the issue is here and here, I think we might need to go with some Spearman on this. And if you look at the Spearman value, it is actually higher. Once again, that is not the way to decide it, but it does kind of indicate to me that maybe I'm on the right track, that the Spearman's picking up on something a little bit better. Probably the downweighting of this outlier, and there's a very strong Spearman relationship. That is Very strong Spearman, and it's helping with the issues of the heteroscedastic, differing spread, and the outliers, things that do not follow the trends. Okay, let's do the last part here. Question number 2. Let's take a look at question number 2. In question number 2 right here, we are going to load up. I always have this fear I'm not streaming. We got 3 people watching. Yes. Awesome. Say hey in the chat if you're watching. In question number 2, we're going to load up the movie data set. This is inside of the reg class package. So the movie data set right here is in reg class. And let's take a look. We're going to go right here, movie. And we run it, and the movie data set appears. This is not loading a file from your computer. It's loading a file. Michaelos, good to see you here. Let me throw you 100 points. Thank you for being here. If you have any questions, let me know. If you're like, hey, Brian, Kirsten, good to see you here. If you're like, hey, Brian, can you explain this? I don't get this. Just let me know. And I'll go back over stuff. This is loading a data set that's been attached to your computer due to the package reg class. Reg class loaded this data set, and the way to confirm that is, 1, if you're typing and you don't see this, you have not loaded library reg class. But notice at the end of this how it says reg class, and that means it's inside of reg class. If it doesn't load when you do that, make sure you type reg class. If that doesn't load, make sure you've installed reg class, and you only need to install reg class one time. That downloads it to your computer. You're welcome, Mikolos. Let me take another 100 points. Hopefully this is helping, kind of talking about what this output says. Here we are with the associate function, which is going to make all these really cool graphics for us really quickly. We want to predict, which makes this the y variable, the response variable of interest, from weekend, which makes this the explanatory variable. Which measure, Pearson or Spearman, is appropriate? So do remember from earlier, we have some notes on when we use each one. We've got ideal Pearson is a linear, no outliers, minimum heteroscedasticity, which is differing spreads. We want homoscedastic. We don't want heteroscedastic. So the Spearman can handle the nonlinear, so monotonic, but still it'll be nonlinear, but monotonic means one direction, if you're a band, and it can handle outliers, and it handles heteroscedasticity. We generally use it when there is nonlinearity or outliers. Well, let's see what we got. Do we have any of those issues? We're going to go down here to the associate command right here and see if we see those issues. Associate function, let's go right here. We need to go total is the y, tilde, and this is the formula format. Make sure to do the capitals. Sometimes it doesn't hurt to copy paste. Do notice if you click it, it's going to show you if it's the exact same, one of the neat features. And then data equals, and then we have the movie data frame. So this is your format for it, y tilde x comma data equals. The tilde is right next to the 1 over here. So if you look next to your 1, you have a tilde. So that's the formula y tilde x. It makes this. This is the y, this is the x, and then your data is where the vectors are inside of. And you can see right there, movie and total. These are the two we're using, weekend and total. There we go. And let's take a look. What do you see? I see something right here. Let's take a look at it. I see a few issues. We only probably have one thing right here that's good. I see this. That's okay. But I was taught to draw on my graphics. Thank you, Dr. Seaver. I see some stuff. I've seen things. What do you think, Pearson or Spearman, and why? It's a good test question. Pretty clearly has some issues. And if you cheat, once again, you could look over here and 95 and 91. That's a pretty big difference. I should have mentioned also we have an estimate of the p-value down here, and they're both estimated to be statistically significant because we think when I create a plot, it doesn't have it showed in the plots function in the second bottom like yours does. Oh, yeah, let's fix that. Here, I'll change that right after this. Mikolos, you're using the default probably way of doing it, and I don't like that. I'll show you how to do that. Go here to Tools, Global Options, and you want to go to... Where's it at? I know where it's at. I've done it. I think make yours look like this. This is what I think is on. D-click this right here. Take a look at what I have on my screen here, Mikolos. This is Tools, Global Options, and then go to the R Markdown, and then it won't appear below. I like it to appear in this window on the right. I just like it that way. It's the way I like to set mine up. But you can make that change, and it's just like a preference. So tell me if that works right there, Mikolos. And thank you so much for asking that. And just let me know, like, hey, Brian, this doesn't look like this. And hopefully that does. So you can pause on the screen right here, But I think this is the change you have to make. And I don't think any of these options really matter. I need to update my R. Want to be updated again. I update all the time. Multiple semesters. I've been like going since like R 3 point something. Before just came out like a year and a half ago. So when I'm like, R just 4.0 came out like a year and a half ago. It's not brand new anymore. It's not brand new. So this definitely looks like a Spearman to me because of outliers, heteroscedastic. It's got the linear component, but the other ones, like as soon as other issues start to get big, you're like, okay, it's linear, but we got some heteroscedasticity. It's thicker here than it is down here where it's really thin, then it starts to thicken out. We don't want differing spreads, different, scedastic spread. We want homoscedastic spread, same spread throughout. And yeah. Oh, now we're going to log it. Ooh, take the log 10 of that. Pretty sure we can just throw the log 10 into it. That's the last question. Oh, sad times. Associate. I don't log 10 it much. Log 10 is a function, specifically that log 10 stuff. And we are doing the total as the y, and we're taking the log 10 of this right here. Data equals movie. Oh, that's even more Spearman than ever. And it doesn't change it, especially the Spearman. It helped the Pearson, but notice, yeah, this is one advantage of Spearman correlation. Yeah, notice how Spearman correlation is the same value. So because when we do this, I had to uncheck show output inbox. Awesome. Great job right there. Glad it worked out. Since we're applying a constant transformation to the values, it won't change the order they're in. So remember, Spearman rank correlation keeps things in the same order, it's by the order. Like when you rank correlate this value, it's 1 on the X and 1 on the Y also. And then this one would be up towards the 309. That's the 309 for the Y's. That's the 309s for the X. So it doesn't matter. Rock, what do you think?
It doesn't matter.
If we look at it this way or this way, because this value up here at the top is still value 309, and that's where it would be over here. It's like one of those values. It doesn't matter that it's been transformed. It still would keep its position in the line with all other variables. And I think that's got it. What other questions do people have? This is a good 50 minutes or so of review. Good activity, good going through the notes right here. Make sure you know what all this output is. We talked about how this is the Pearson value of correlation, the Spearman value of correlation, the p-value, which tells us whether or not statistically significant, estimated from the permutation procedure. There's no permutations as extreme or more extreme than our result, which this is our result. And this is a result just as extreme, and none of the random permutations are outside of these bounds. So the p-value is estimated to be 0. That's not an actual p-value via a parametric procedure. It's estimated via a randomness procedure, or parametric approach, I should say. That means using like normal curve or chi-squared curve. And so here's the other value of correlation, the Spearman rank correlation, which is going to downweight our outliers, handle the heteroscedasticity, and be only for monotonic relationships. And this has a p-value estimated to be 0 also because there are no permutations as extreme or more extreme. These are the random permutations. Here's the value at 0.95. This right here is at negative 0.95. And then we estimate what the p-value is. And look, the p-value is estimated to be somewhere between 0 and 0.007. And that does not contain 0.05. That's super important because if 0.05 is in the range, we're kind of uncertain if it's significant or not. We'd be like, I don't know. Maybe it's significant, maybe it's not. And we would call that an inconclusive p-value estimate because we can't conclude that we have confidence it's significant. We'd say, I don't know. And we could show one of those. Let's just show one of those in inconclusive interval real quick, and then we'll finish off right here. We need to find one that's kind of borderline, and it would probably be something like 12, which is number of tattoos in GPA. So we're going to go down here to our code again and run it with number of tattoos in GPA. And this is probably going to lead to an inconclusive interval. And if we take a look right here at our interval, you'll notice, aha, we did it. Notice how our p-value is not significant, but we're not certain about that. We're like, the p-value is, we estimate it to be 0.058, but it's somewhere probably between 0.039 and 0.082. So what do? If 0.05 is in the range, meaning it's inconclusive, we need to increase the permutations. That's why we have the argument, another comma, permutations equals, and why not 2000? This will make a narrower interval, and guess what? Now our interval is completely above 0.05, and it could be completely above or completely below, but it is conclusive when it does not contain 0.05. So now we have a conclusive interval to conclude that this Pearson correlation between the number of tattoos someone has and their GPA is likely by random chance. If you have any questions, email me. That's it for today. Have a great House on Friday. Bye, everybody. Bye.